So we have quite a few reactions to start today, still dealing with alcohols. Let's start by looking at Grignard reagents. So Grignard reagents, what we do is we start with an alkyl halide and we add to that mixture magnesium. So we're going to add this to a reaction mixture to make this in situ. So what that means is in solution, and then you immediately add whatever you're going to react with that after you've made your Grignard reagent. This is kind of like making a nucleophilic R group, so a C minus. It's kind of the closest we can get to that, because what happens here is that your magnesium pulls, it's more electropositive, so we are allowing that to have a partial positive charge. The fact that your Br or X is usually pulling electrons more from the other side means that this is a even better nucleophile at that point. However, Grignard reagents are very sensitive to anything that's a proton donor. So waters, alcohols, they will not work with carboxylic acids for that reason. So here's how we can work with those. If we start with a ketone or an aldehyde, keeping in mind that when we do work with a ketone or aldehyde, again, your partial positive charge is on that carbon and the partial negative would be on that oxygen. We have an R sort of minus right here that will come in and attack where that positive charge is, leaving you behind an R group. So let's look at the mechanism here. So the electrons that are making up this bond are going to move because why? Well, because we've got a sort of nucleophilic bond there. If you want to even consider it sort of so that you would have like a negative charge or a partial negative charge on that guy, and MgBr is its separate thing. Sorry, I can't seem to write today very well. You've got a positive charge there. So I just draw it though with this bond is coming over and attacking this partially positive carbon. So you've got electrons that are sort of open there and they're attacking where that carbon is. Electrons then go up, and when they do, they will seek out a proton source as soon as that's provided. So that's how you quench or end the reaction right there. And that's what gives you this OH. So the R group that you just put down is 2 carbons long, so that's 1 and 2. And some of these get a little bit hairy, so it gets a little bit more difficult to determine how many carbons you're adding. So when in doubt, just count it. I say when in doubt, count it out. Do that, okay? Don't be afraid to, look like you have to count. It's okay. There's a reason why we start with that in kindergarten first thing, right? Because that's a very fundamental thing for us to do. Okay, next we move on to Grignard reagents with esters. These are very similar to what we just saw. The difference is that they work twice. So if we start with an ester, we get the R group that is there twice on that same carbon that is involved in the ester right there. Okay, so let's start by looking at our mechanism. It's very similar to what we saw with lithium aluminum hydride. So we start here, the electrons go up to where that carbon is again, and we shift those electrons then up to the oxygen. Sorry, I can't highlight on that far left of my screen here. But as you do that, then you've got a negative charge on the oxygen, electrons fall back down, and that leaving group here is going to leave. And then we have a regular ketone. So same thing happens as what we just did above. Electrons go here, bounce up, and then the negative charge from the oxygen is going to come and grab that hydrogen. Electrons go back to that, making water, and that's where your OH comes from. So the 2 R groups that you had on your Grignard reagents, so there's 1, there's 2, end up being right here and right here. So if you have 2 of the same R group coming off of a carbon that's attached to an OH, that tells me this is what I need to do for a synthesis reaction. Okay, and as a reminder, Grignard reagents cannot be used with carboxylic acids. So with alcohols, we're going to introduce a concept called protection groups. And what these protection groups do is kind of what the name implies. It protects a particular functional group so that you can do other transformations without disrupting that functional group. Or you can do it in a situation where you wouldn't otherwise be able to complete a reaction with that functional group present. So with alcohols, what we use is TMSCl most frequently, and that's trimethyl silane chloride. So if you have an alcohol, you would add TMSCl, and this is triethylamine. So triethylamine is a nitrogen in the center with 3 carbon ethyl groups that are coming out from that spot. Keep in mind this has a lone pair of electrons right there, and so it can act as a base. We also refer to this as a TEA, just TEA. So not to confuse that with actual tea that people drink. Anyway, what that does is that replaces the hydrogen with this group right here. Then you can remove that with TBAF, which is tetrabutyl ammonium fluoride, if I remember correctly, and regain your alcohol in that case. So here's a potential use in synthesis, for example. So in this case, what we're going to do is we want to take this bromine functional group right there, so the alkyl halide, and eventually we're going to use that and turn it into a Grignard reagent. Well, remember, Grignards are sensitive to any type of alcohol or water, so any type of proton source will not work in the presence of a Grignard, or a Grignard won't work in the presence of an alcohol. So instead, what we need to do is we need to use this TMSCl and put a protection group on our alcohol functional group. So that alcohol functional group that's right here, we're going to put TMS on the end of that. And then, and only then, are we going to start to change that to MGBR. Now we have MGBR down here, so we've got our Grignard reagent. You can add a ketone, get your final product here, and then we just remove that TBAF. We remove that TMS with TBAF. So we end up making a diol in the process. Okay, so that's an example of one. We'll look at others later, and we'll look at the different protection groups and protection types of groups for different types of functional groups. So they're not all the same for sure. Okay, so now we are going to start talking about different types of substitution and elimination reactions, and most of these you've seen, so hopefully this is a nice review. Remember, we can use SN1 or SN2 types of substitution reactions. Generally speaking, we prefer SN2 reactions, so I'm going to go into much more detail there, and I'll get to that in just a second. So let's look first at what we have with an SN1 type of reaction. So in this case, we've got a central carbon right there with 3 ethyl groups coming off of it, as well as an OH right here. If we use like HX, BR, for example, you would just end up with that BR at that point right there. Now, remember, these work best with tertiary alcohols. So mechanism, we should already know that. So the mechanism is that we're going to grab a hydrogen from your acid that then leaves, so the water that's here leaves, leaving behind a carbocation that can then be attacked by different nucleophiles, because you still have a nucleophile from this guy over here, right? And so you end up with an alkyl halide at the most substituted carbon. The reason why we don't like to use SN1 very often, especially for secondary carbocation or secondary alcohols, is that you can have rearrangements happen. So remember, let's say that we go through this process and our OH reacts with our hydrogen, and then that OH2 leaves. What we end up with right here is that we have a carbocation with a more stable position next door to it. So if we were to have a hydrogen right here, we have a hydride shift that occurs. And so that carbocation that's right there is now what you actually are reacting with your nucleophile, giving you a much different product, which is fine if that's what you're trying to make. But if it's not, that's probably not what you want to get as a final product. So especially when it comes to secondary alcohols, usually we try to get that to work with SN2 mechanisms. So let's look at SN2 mechanisms in general. Remember, things that are primary alcohols. So if we have just a primary alcohol, a vast majority of the time, those are going to go through SN2 reactions anyway. But when we have a secondary alcohol, we also have two hydrogens there, so we don't have a stereospecific product. Okay, so remember though, this is a concerted mechanism, so it's coming in from the opposite direction. When you have a nucleophile that comes in, it's going to come in from the opposite direction from where your leaving group is leaving. Now, if you're going to use a HCl or replace this with a chlorine ion, you usually want to use zinc chloride. Okay, so that needs to be catalyzed a little bit better. So let's look at other avenues to use with SN2 types of mechanisms, okay? So we're going to start using something called pyridine quite a bit. Sorry, let me blow that up a little bit better. So pyridine, as you can see right here, is a good base. Why is this a good base? Well, if you notice, there's a lone pair of electrons that are here. It's not a strong base. If you have a strong base, you're going to potentially cause elimination reactions to occur. You don't want that to happen. Unless you want that to happen, you want to make sure that you're removing hydrogens that are needed without making really good nucleophiles. So that's the purpose of using pyridine. If you recall this from previous semesters as well, if we have a stereospecific alcohol, we can use what's known as tosyl chloride. So that's what TSCl means. And what that does is it removes the hydrogen and replaces you with a tosyl group. And then that makes a really good leaving group. This does by itself. So a nucleophile can come in and you get the inversion product at that point in time. If you want to look at that mechanism in more detail, I'm trying to blow it up again so you can see there. So what we have is we have the electrons from oxygen going over to sulfur, and that chlorine leaves. Okay, so that now can be your nucleophile later. You don't have to put in another nucleophile, that's fine. Or you can just leave it as is. The pyridine comes and grabs that hydrogen. The electrons go back to the oxygen. Sorry, that's really tiny. And then you can either put it in a new nucleophile or that's in greater abundance than the chlorine, or we can use the chlorine that's there. Nucleophile then comes in and displaces that tosyl group, and that's where we end up getting the inverted product there. And again, I'm pointing out that if you have a strong base, what can happen instead is you can get an E2 elimination where the hydrogen is removed, electrons come down, this comes off, and you end up getting that double bond. So just be aware of that. That can also happen. Other SN2 types of reactions, let me move this just slightly over here, can include that with PBr or PCl3. Usually I see this with PBr3 the most, but you can use either one. What these do with PBr3, again, this is going to give you a good leaving group and leave behind the Br. If you use PCl3, it's going to leave behind a Cl. So the mechanism involves these electrons from oxygen coming to the phosphorus, then bromine leaves. Now bromine is going to be your nucleophile. Okay, that's the next step. So bromine is then going to come in here, and that leaves, and bam, there's your bromine. Okay. SOCl2 is very similar to this. So in this case, what we have is the OH that's right there. With SOCl2, this takes pyridine, gives you that chlorine there in the back. So very similar mechanism. Oxygen's electrons come in here to the sulfur, chlorine leaves, that's going to be a nucleophile that you already have. Pyridine comes in and removes that extra hydrogen. Electrons go back to that oxygen. And then you have a chlorine that you generated earlier come in here. This is a great leaving group, and when it leaves, you get that inverted product. So those are very similar. Be aware that there's also something called POCl3. So I call the SOCl2 socyl, and I use POCl3 as pocyl. And the advantage here is the fact that you are at 0 degrees. Most elimination reactions, remember, happen at a higher temperature, not a lower one. So in this mechanism, what we have as a product is we end up getting that elimination product. So the electrons from the alcohol come to the phosphorus. Again, this kicks out that chlorine. Pyridine removes the hydrogen there from the alcohol. But what happens next is that another pyridine is going to remove the hydrogen next door. These electrons go up there, and there's your final product. Sorry, I did draw that incorrectly, so just a little bit over. That's where that's supposed to be. Okay. Oh, and this also leaves there, since I didn't draw that in as well. Okay, so the last thing we need to deal with alcohols is that of oxidation reactions. Sometimes in different textbooks, I will see CrO3, H3O, and acetone. In other textbooks, I see NaCr2O7 in the presence of H2SO4 and water. Either of those conditions make H2CrO4 in situ. So sometimes you'll even see textbooks that have this. If you're taking an MCAT or anything like that, they're all the same thing. It's getting to the same thing, so don't let that confuse you, okay? These oxidize to the fullest possible extent. And what is a possible extent is if there's a hydrogen left on that carbon, it can still oxidize one more time. So let me show you what I mean by this. If we have a secondary alcohol right here, we have another hydrogen here, but everything else is carbons or oxygens. So when we oxidize with NaCr2O7, then we can end up getting a carbon here with another bond to oxygen, so you get that oxidized product, but there's no more hydrogens there for it to work with. It's done. On the other hand, if you have a primary alcohol, we have 2 hydrogens here. Each of those can be removed. So we can keep oxidizing until we end up at the carboxylic acid state. Okay. If instead you have a tertiary alcohol, like we see down here, there are no hydrogens on the carbon right here. It cannot oxidize. It is done. Okay. So let me go back then to this reaction right here, okay? PCC stands for pyridinium chlorochromate. The same way that we had Lindlar's catalyst as a sort of a poison version of palladium on carbon, PCC is kind of a less active version of this same chromate type of oxidation. It stops even with a primary alcohol at just the carbonyl. So you just get this C double O bond. It won't keep going all the way to the carboxylic acid, which is an advantage if you're trying to make an aldehyde. Now, there is a greener version of making oxidative products that's like the PCC, and that's called the Swern oxidation. And so that's going to use DMSO, COCl, and then all that's in parentheses 2, followed by TEA, and that will also give you the desired product here. I know that's a lot. You may want to go back and review this and try to write down the notes that you want to, and then look at the mechanism again, pause it at the beginning, and see if you can sort of approach those yourself. So good luck, and thank you very much.